my presentation is about analysis carried out on Roman Terra Sigillata data that were collected during the Archaeology project. Okay, briefly I present the project. Is an H2020 project that will end at the end of May this year with many partners throughout Europe. The goal of this project is to create automatic recognition of pottery through artificial intelligence in order to support archaeologists in finding comparison between pot shares without using paper catalog, but using a mobile application. For doing and for reaching our goal, we decided to work and to develop a proof of concept that use as test classes the Roman amphora, the Roman Terra Sigillata coming from Italy, Italian Terra Sigillata, Hispanic Terra Sigillata, and South Gaulish Terra Sigillata. And then Maiolica coming from Italy and Spain. For achieving our aims, we create a big database with a lot of information related to the ceramic classes I previously explained, with all textual data, but also 3D model extracted from the drawings that are inside the catalogs, and geographic data related to origins and occurrences of each pottery types, and many other visual information. The core of the system is based on artificial intelligence, on the developing of two different neural networks that works with appearance-based recognition for allowing the recognition of decoration in the surface of the pottery, and another neural network that allowed the shape-based recognition, extracting the profile of the pottery. All this is done with just one image. But the core of my presentation is about the data we've collected during this work. Many data, mainly related to origins, occurrences, typology, workshop that produced a certain type of pottery, and so on. In the case of the Terra Sigillata, we were able to collect at least 250,000 different records about distribution of Terra Sigillata. So we start to work with this data in thinking about a sort of big data approach to this kind of data. So the data we use are mainly the data that are into our database, but some data come from the Roman Germanic Central Museum website that collect many thousands of data related to Terra Sigillata through the automatic digitization of Conspectus catalog, through the digitization of the Kenrick catalog about the stems of Terra Sigillata, and also using Sparkle endpoint for querying information from our database. In this way, we were able to create a network structure that is given by linking together location where ceramic was produced and location where the same ceramic were retrieved. At the end of our work, the network is made of 3,411 vertices, 50,645 links, and more than 2,000 data with frequencies. That means how many shards of that type were found in a certain location. So this is all the data we have. The stamps, that means the workshop that produced the Terra Sigillata, which types were produced, where they were produced, where they were found, the chronology of both the types and the stamps, 3D reconstruction, 3D models in order to have dimensional data about the pottery itself, and also other kind of data. All the analyses were carried out with R, and because of the fact that we want also to visualize through our website all the data, the outputs were provided in a JSON in order to permit a better embedment into the web application. So in the future 15 days, part of this data analysis will be visualized through our website and they will be openly available for everyone. So, starting from the work, the first idea was to find networks between producers throughout Europe, throughout the Roman Empire, in order to understand the way in which they could be produced and commercialized, and then also to identify the temporal breadths into the data. As I said before, the structure is given, linking together location where ceramic were produced to location where the same ceramic were retrieved, with a sum of 3,853 different locations all over Europe, Middle East, and North Africa. This is the first result of the overall network, all the data linked together in the way I explained before. So, what's the meaning of our previous image? Vertices are a location where ceramic are found. This is independent from the fact that ceramic were produced or simply found in the specific location, and attached to each vertices we have the name of location, obviously latitude and longitude coordinates, and also the number of the edges that start from the vertices. So the out degree of each vertex, and also the in degree of each of these vertices. Another important aspect is that we are able also to link, and so to link location, and this permits also to understand which kind of ceramic types move from one site to another, and which kind of workshop move their commodities from one location to another, and also the chronology of this production. In order to understand and to identify the communities in our network, we applied classification and clustering technique in order to group the location, the vertices that are densely connected internally, but poorly connected externally. For doing this, we apply two different community detection algorithms. One is based on eigenvalues, sorry, and the other on random walls. And this is the result. The different color means the fact that means the different communities. So red is one community, purple is another one, and so on. Which is difference between these two algorithms. The first one is able to detect network, maximizing the possible division between the network. Meanwhile, the other one, the word trap clustering algorithm, follow a complete different approach because works are more likely to stay within the same community that going outside the community itself. It's important that analyzing the results of these two different algorithms, we understand that the results were very similar. This, from our point of view, indicates that communities that are identified are really well defined. I have to say about this that in this moment we are working with the math department of our university for understanding a way for detecting the best approach in order to analyze the results themselves and to say which of in general which of the algorithm applied is the best one that fits better to the problem. So we are waiting for the result of a series of master theses related to clustering detection. Anyway, once we were able to detect the community, we start asking ourselves which vertices are more important, which are central in the network, and that is why. That is the archaeological explanation of our analysis. So we work on the out degree and in degree of each vertex, and we start working with the page rank algorithm. The result is this one. The dimension of each point now changes on the base of PageRank algorithm. How it works? PageRank simply count the number and the quality of link of each vertices. PageRank is at the base of the Google algorithm, for example, that compute the links between web pages. So the assumption is that the more important vertices are likely to receive more links from other, in many cases, important vertices. So a vertex has a high score in PageRank if many vertices point to it. Otherwise, the score is lower. In this way, we are trying to detect the most important vertices in each community. The second, how many time? 5 minutes? Okay. The second aspect was to define the breaks, the chronological breaks in a long period that starts from 40 before the Common Era to the end of the 3rd century of the Common Era. We use the Jank natural breaks optimization, and we use the lowest data in the chronology range with a defined number of breaks, in our case 5 breaks. In this way, we were able to minimize the variance within each categories, and in the same moment maximizing the variance between the categories. This permits us to create a graph with the frequency of production in view opening of each workshop, and in red the moment of crisis, I can say, when the workshop closed. We also compute the average lifetime of each production in order to follow the period of expansion of the production and the following periods when the production period lifetime is shorter. We also analyze the distance covered by the productions. What is of interest is obviously that many of the ceramic are close to the place where they are produced. That is obvious. Anyway, there is another peak around 1,000 kilometers that is interesting to understand, that is mainly related to the way of transportation of this kind of commodity. Anyway, we have to analyze more in depth this field. Obviously, we are able to visualize the changes in chronology from the starting of production to the end of the production. In red, you can see the production center, and so you are able to visualize the change, how the pattern of this kind of production changes through time. So to conclude, we start to work with network detection for each different period, for understanding how production changes. So this is the general overview of all the networks in four different period, both with the application of the algorithm and with the application of PageRank algorithm, and then to visualize the different step of the production with the main sites in the different four periods. So you are able to see how the production changes through periods. So, in order to conclude, from my point of view, what's of interest is the fact that if we are able to work with huge amount of data, we can see different insight in our data, analyze in a different way some aspects. We will start to work also with relation with types in order to see which types are related to each network and so on. And in the future, if data will be available, we are interested in working with context in order to put together different types, different classes of pottery. For example, analyzing cluster of amphora production and terra sigillata and other kind of production in the same period. So this is the final slide. If you are interested in understanding a little bit more our project and all the aspects that I explained, we wait you at our final conference at the middle of May in Pisa. Thank you very much.